Hey guys, this is Mr. Banner. I'm going to help you go through some of your energy packet notes. Let's go ahead and get right into it. I don't want to take too long. It's about energy. So what is energy? Energy is the ability to do work, and you might have learned earlier in life, or maybe perhaps when you think of energy in the food that you eat, you think of it as calories or the big calorie, which is a kcal. Right? A big calorie is a kcal. But this is the English unit. We're not going to use that. The SI unit is the joule or capital J, capital J. So if we were asking how much energy was this, we'd say 100 what? $100, 100 Kit Kats, 100 newtons, not newtons, but 100 joules, right? And we can break down that unit and look at what that actually is, okay? But energy is the ability to do work, right? If I don't eat, if I don't get enough calories, we're going back to this English unit, if I don't get enough calories in the morning, I can't do any work when I go to work, right? And work also has a very specific definition, which we'll get to in another lecture. All right. Conservation of energy. The total mechanical energy is the sum. Sum means what? You're adding up, right? Of the kinetic and potential energy. So total energy, another way to say total energy is mechanical energy. So total mechanical energy is sometimes just put as mechanical energy. Is the kinetic energy, Ke, plus potential energy. And there are lots of different types of potential energies. Your total mechanical energy is always conserved. That's very important mathematically. We'll talk about that in a little bit. Okay, so basically, you are never creating new energy out of nowhere. You are not destroying the total energy in the universe. All you are doing is converting. You are always just converting. And when we say that we are converting something, mathematically what that allows us to do is it allows us to do this. It allows us to set these equal to each other. And this specifically, and I want you to go ahead and take note of this, this is the max kinetic energy of a situation is always going to be equal to the max potential energy, as long as we're not factoring in things like friction, wind resistance, things like that. So in ideal situations where wind resistance and friction is negligible, we say that these two are equal to each other because of the conservation of energy. Okay. Now, kinetic energy, you might remember this from middle school, is 1/2 mv squared. Potential energy is mgh. So we know from algebra that if A is equal to B and B is equal to C, then A is equal to C. So we can just cancel these out and just set these equal to each other. From here, you can see that algebraically, we can do some cool things. mv squared equals mgh. And we're going to talk about what gravitational potential energy is in just a second. But you can see that I can solve for the height, I can solve for the velocity without even needing the mass, because watch what's going to happen. Let's say I want to solve for height. Divide by mg on both sides. So we have 1 over 2 mv squared over mg, and look what happens. This m cancels out, right? So we don't even ever need the mass. That would be equal to our height. Okay. So let's talk about potential energy. This is gravitational potential energy right here. Let's see if there's a slide here that talks about it. Okay. Mechanical energy. Kinetic energy is the energy of motion. So kinetic, whenever you think kinetic, you should think moving. Right? Kinetic, like kinematics. It depends on the velocity and the mass. These are the things that affect kinetic energy. And if you look and you think about algebra 2 and you think about parent functions, which one of these variables here is going to take the overall behavior? Well, you think about the thing that if I plug a number into it, like if I plug a number into mass or if I plug a number into velocity, which one of these is going to change the kinetic energy the most, right? So try it. Plug a 2 and a 2 in here. This is going to become a 4, right? So the velocity is going to change the kinetic energy the most. If you look at gravitational, this is little g, this is gravitational subscript, is mgh. All of these are going to affect the potential energy gravitational the same. There's no square, right? All right, now, how do these things convert into kinetic and potential energy? So if I have an object here, I have an object, and I have like some sort of cliff or something like that. It's this one right here. You can see that if I do a lot of work to lift it up this ledge versus this ledge, the height is greater, right? So this one, we'll call this A, we'll call this B. The height of A is much bigger, right? So height A is bigger than height B. So which one of these is going to have a greater gravitational potential energy? If the mass is the same, and we're on Earth, so G is going to be 9.8 meters per second squared. the height is going to be greater for here, so the gravitational potential energy is going to be greater than the potential energy at B, right, because of the height. So you can see that. And what do we mean by potential energy, right? If I were to drop this off the ledge a little bit, this would accelerate towards the ground and convert totally into kinetic energy by the bottom. So which one of these would have a greater kinetic energy, A or B? Well, since we know mechanical energy is potential energy plus the kinetic energy, right, we know this has to be conserved at all times. This is always conserved. Then we know that the kinetic energy max at the bottom for A would be greater than B, because this has a lot more potential to smash some sort of little bug or something at the bottom, right? So if I have a little ladybug on this one versus a ladybug at this one, this ladybug right here will potentially be splatted much more than this one, right? Because it had much more potential to speed up and gain kinetic energy. All right, here's some types of mechanical energy. Gravitational potential, which is what we were just talking about. Elastic potential energy, so this is like a trampoline or a bowstring, or even like a spring. Kinetic energy is just moving energy. All right, so let's take a look at some graphs of this stuff real quick. All right, move some of these guys out the way. All right, so if I toss a basketball up in the air, right, if I toss a basketball straight up in the air, at the very beginning, the mechanical energy, let's look at our key over here. So our total energy, J, it's going to be right here. And it's all because of the height. This must be starting at some height that's not zero, right? So it has some gravitational potential energy. Potential energy here. So 100% of our energy right now is in gravitational potential, right? So let's kind of think about it in terms of mechanical energy. Potential energy plus kinetic energy. So right now, 100%, I'm going to go ahead and type out 100%. So our mechanical energy is the total, so 100%. At the beginning, we have no kinetic energy, right? We have no kinetic energy. So this 100% has to come from just potential, right? When we get to the very top of the path, right, we have the red line's potential energy. It has the greatest height it's going to have. So 100% of our energy here is going to be potential energy. And look at kinetic energy. We remember parabolic motion. We throw an object in the air in a parabolic path. What does it do as it gets to the top? It slows down, comes to a stop. Because it comes to a stop, our 1/2 mv squared is our kinetic energy. If we plug a 0 in here, this whole thing goes away, right? So we have no kinetic energy at the top. So what happens if there's no kinetic energy at the top? 100% of our mechanical energy at the top has to also come from potential energy, right? Now look what happens as this thing starts to descend. As it starts to descend, we are picking up speed, right? So this velocity is going to increase. The velocity here is going to increase, increasing the total kinetic energy. Right as we're about to hit right where we started, notice the potential energy drops to almost 0, getting really close to 0. But our kinetic energy hits its maximum, right? So the max kinetic energy is going to be equal to approximately what our top kinetic energy was, our potential energy. Let's look at another example of this over here. So an object coming down a ramp right here, right? At the very top, it's got 100% potential energy. Total mechanical energy, notice that they're the exact same, right? As this rolls down, it's going to lose its potential energy, so it's going to go away. It's going to go away. And whatever I lose here is going to end up becoming my kinetic energy, right? So I'm not losing energy at all points in time. If I were to take this away, if I were to white this out, you would notice that if I add these two bars together, stuck them together, look what I end up getting. I end up getting the exact same height as my total mechanical energy bar, right? So that's what's happening as this thing comes down the ramp. There's some roller coasters here. You can see at the top, it's all potential energy. So my mechanical energy is all potential. When it comes down at B, I have some height, so my potential energy is still pretty high, but my kinetic energy is making up for the difference now. Look at the yellow bar. always 100%. The bottom here, when I've lost almost all my height, look at almost all of my energy is kinetic energy, right? Potential energy a little bit because it's not at ground level, right? All right. All right, let's try this problem out real quick. An object has 25 joules, so I go through and underline joules is energy of potential energy. So that's gravitational. Potential energy, gravitational. And 40 joules of kinetic energy. So this is kinetic energy. What is the total mechanical energy it possesses? So mechanical energy equals question marks, right? And we told you earlier in your notes that the mechanical energy is just the sum of the two, right? So all I'd have to do, mechanical energy is equal to my potential plus my kinetic. Let's go ahead and just plug them in. So 25 joules plus 40 joules, and we end up with 65 joules. Okay, this is my mechanical energy. Baby bird falls from its nest to the ground, hitting the ground 15 meters per second. This is our velocity final. I need to leave, so he did not die. How high, that's height, is the nest? So how can we figure that out? Well, I have to use this concept up here. And I know that my mechanical energy is the sum of potential energy plus kinetic energy. If I know that the fastest I'll be going is at the bottom, right? If I drop something, the fastest it's going to be going is right before it hits the ground, right? I know that the kinetic energy max has to be equal to the potential energy max. And if these two are equal to one another, what are they going to add up to be? Well, they'll always add up to be a big fat 0, right? So if I want to solve for the height, which is going to be locked up in here in potential energy, I can subtract this to the other side, right? I can subtract this over here. So let's go ahead and do that. Minus my potential energy. So potential energy is equal to my kinetic energy, right? Now we can plug in our equations. mgh, negative there, is equal to 1/2 mv squared. Okay, and we're solving for height, so let's divide by negative mg. Height is 1/2 mv squared, and we can also just put down here in the denominator mg. These cancel out. Let me get some space here. Just move this over so we can see a little bit better. Okay, what am I plugging into? What am I plugging into v squared? I'm going to rewrite this so it's nice and neat. Okay, what am I plugging into v squared? That's 15. Should square that. And what's 2 times gravity, which we're just going to make easy and make it 10. All right, now 15 squared. You don't know that off the top of your head, always use calculator. So 225 over 2 times 10, which is 20, divided by 20. You get 11.25. So this is about 11.25 it's meters because we're looking for height, right? All right, number 5, let's do this one real quick. Rock falls 15 meters. How fast is it going when it hits the ground? So you really don't need much for this, right? 15 meters is our height. How fast is it going? This is velocity final equals question mark. This is the exact same concept here. So we're going to go ahead and just do a shortcut. mgh, that's our potential energy max, has to be equal to our kinetic energy max, so 1/2 mv squared. All right, so we're looking for how fast, so we're looking for v, right? We're trying to isolate v. So let's times 2 mgh with mv squared, divide by m. So that's going to divide by m. This m is going to cancel out. 2gh equal to v squared. We'll square root both sides. So the square root of 2 times gravity times my height is equal to the velocity. So 2, what's gravity equal to? We're going to use 10 for simplicity. And our height was 15 meters, right? And that's our v. So 20 times 15 to the square root of 300 is equal to my velocity. All right, that's 17.3 meters per second, right? So you're using the conservation of energy, almost a momentum. Conservation of energy to kind of link these two equations together. This is the important part here. You're using the conservation of energy to know that you can link gravitational potential energy equation to to kinetic energy. Let's speed this up a little bit. So the skateboarder is going to have a very similar problem. I won't go over that one because you kind of know the basics from doing that problem we just did right there. You know the relationships. Try to look through this and see if you can link the relationships we just talked about. Where is potential energy the greatest? So where is this at? Where is kinetic energy the greatest? And where are they equal? Where is potential energy equal to kinetic energy? Where are they equal? Right? At what point, or what single point is my potential energy gravitational going to be equal to my kinetic energy? Where is total mechanical energy the greatest? Right? So think about that. This one's actually kind of a trick question if you think about it, right? So keep that in mind. All right, so here's some more questions. I kind of want you to see this right here before we go. Check this out. So you can kind of see if I put the skateboarder on the ramp here, drop down. Check out what's happening. Look, you see the speed is increasing as you go down. So what energy is increasing as you go down? Well, don't ask, just look. Look at the kinetic energy going up, potential going up as she goes up because it's getting further from Earth. A lot of potential to fall and break a lot of good bones. But look at the mechanical energy. Mechanical energy is not changing whatsoever. You add these two bars up at any point, these two bars put together would equal the height of this bar. There you go, would equal the height of that bar. There you go, right? Now you see this thermal energy right here, that these kinetic and potential energies can be converted into thermal energy through friction. And we'll talk about that when we get into work later on. Okay. I hope this was helpful. If it was fast, because I try to go pretty quickly, you can pause this and rewind it anytime you want. Good luck.